In this video, we're going to talk about how to solve rational inequalities. A rational inequality is a statement involving rational expressions that includes an inequality, either less than or greater than, or less than or equal to, or greater than or equal to. Suppose we want to solve this inequality right here. Okay? Well, a mistake people often make is to quote unquote cross multiply. Multiply both sides by t plus 1 and t plus 8, resulting in the expression shown here. The reason that that's a mistake is because sometimes t plus 1 is positive, sometimes it's negative, sometimes t plus 8 is positive, sometimes it's negative. Multiplying both sides by both of them does funny things with the inequality, because we know multiplying both sides of an inequality by a negative quantity changes the direction. So we can't do that. This right here is wrong. Okay, so instead we have an algorithm, a step-by-step process. What we do first is factor denominators and get each of the rational expressions over a common denominator. Then we determine restrictions. Then we get all the rational expressions onto the same side of the inequality, expand each of the numerators, and add or subtract as necessary to get one rational expression. Then in step 5, we factor the numerator. Then we do interval testing, specifically with every value of t or x, whatever it is, that makes either the numerator or the denominator equal to 0. Using that number line from interval testing as a guide, we're going to state the final solution, and we have to make sure not to let the variable equal a restricted value. That last point is interesting because when we did inequalities with polynomials, we never really had to give much thought to that. But because we're using rational expressions now, we have denominators with restricted values. We're going to have to actually consider this in this section. Okay? So suppose we want to solve the inequality shown. So the first thing we're going to do, factor the denominators, get each of the rational expressions over a common denominator. Well, the denominators are already factored, so our lowest common denominator is t plus 8 times t plus 1. So we're going to convert 240 over t plus 8 into a rational expression with the denominator t plus 8 times t plus 1. And we're going to convert the rational expression 20t over t plus 1 into a rational expression with a denominator of t plus 8 times t plus 1. Okay? Now, you might say, well, are we multiplying or dividing by a negative here? It's not the same, because what we're doing is we're not changing the value of the left or the right, because we're multiplying numerator and denominator by the same thing. So we're actually leaving those function values, each of those expressions, the same. So now what we're going to do is we're going to determine the restrictions. That's always important. So in this case, we know that the restrictions are going to be that x cannot equal, or t cannot equal negative 8 or negative 1. All right. So now, after that point, we want to get all of the rational expressions onto the same side of the inequality. So we subtract both sides by 20t times t plus 8 over t plus 8 times t plus 1. And we know that that's going to be greater than 0. That we don't change the direction of the inequality when we subtract like that. Now in step 4, we're going to expand each of the numerators and add or subtract as necessary. So when we expand the first numerator and the second numerator, this is what we get. We've got a minus sign in front. Don't forget to put a bracket around that second numerator. And when we distribute the minus sign into the bracket, we get this expression here up top. When we simplify it, we get negative 20t squared plus 80t plus 240 in the numerator. Now we're going to factor the numerator, so we factor out a negative 20, and we can factor the quadratic inside, and ultimately we have this expression right here. Okay? Now we're going to do interval testing. Notice that the values of t that make either numerator or denominator equal to 0 are 6 and -2 and -8 and -1. So we're going to do interval testing with those values. Okay, here we go. And we're going to have 4 values of t indicated, so we have 5 intervals. And if we let t be less than 8, then we have a negative times a negative times a negative over a negative times negative. Is that greater than 0? No, it is not. So we put an x there. If we let t be in the second interval, we get a negative over a positive. We get a negative over a negative. Is that greater than 0? Yes, it is. If we let t be in the third interval, we get a false statement. Letting t be in the fourth interval gives us a true statement, and letting t be in the fifth interval gives us a false statement. Now, you might be curious here, how can we do this testing when we have restrictions? But remember, the restrictions are that t, in this case, cannot equal -8 or -1 from these denominators, but we're not actually testing -8 and -1, we're testing values in between. So we're actually allowed to do interval testing like this. Now, using the number line from the interval testing as a guide, we're going to state the final solution. Make sure not to let the variable equal a restricted value. Now, recall from polynomial testing that we said when the inequality in the original question doesn't include an equal sign, we won't include values on the number line as solutions either, but if the original inequality does contain an equal sign, we will include those values. But we have to remember here the key words are with the exception of the restrictions. Okay, so because it's a little bit more complicated with the rational expression inequalities, a better approach, as it says in red at the bottom, is when in doubt, plug the numbers indicated on the number line to see if you get a true statement. Well, what happens here is if we state our answer in set notation, we get this answer here shown. If we state it in interval notation, we get this answer here shown, and we've not violated any restrictions. Well, let's do one more example. This time we will have an equal sign, and you'll see that it can be a little bit different. So what we want to do is factor numerator and denominator of all of them. So this is what we get. We only really had to factor one numerator. Now we see that our lowest common denominator will be x plus 5 times x minus 1. So we put every rational expression over that denominator. We state our restrictions. It's important to remember that. This will come back later. Remember these numbers. Okay, so once we have this right here, this inequality stated, we get the rational expression on the right onto the left by subtracting. That does not change the direction of the inequality. And then we expand our numerators as shown, taking a couple of steps to expand our numerators. Don't expand your denominators because you want them factored ultimately when you do your interval testing. So don't expand those denominators. But also, don't forget here that we want to distribute that negative sign into that bracket. So we do that, and ultimately we end up with x squared minus 8x minus 29 over x plus 5x minus 1 is greater than or equal to 0. Okay, now we want to do interval testing, so we need to know what values of x make the numerator and denominator equal to 0. We know the values of x that make the denominator equal 0 are -5 and +1. But how about the numerator? Where does that equal 0? Well, to do that, we're going to use the quadratic formula. Okay? So we determine the zeros of x squared minus 8x minus 29. And when we do that, we end up with, after simplifying, 4 plus or minus 3 root 5. Those values of x make the numerator equal 0. For interval testing, it's good to have decimal approximations, even though they won't show up in our final answer. 4 minus 3 root 5 is roughly -2.7, and 4 plus 3 root 5 is roughly 10.7. So what that means is that this numerator of x squared minus 8x minus 29 is roughly the same as x plus 2.7 times x minus 10.7. If you don't believe me, actually expand out x plus 2.7 times x minus 10.7, and you'll see you get a polynomial very close to x squared minus 8x minus 29. Okay, so what that allows us to do, it allows us to make our intervals and to do our testing. Again, we have 4 values for x, and so we're going to test 5 intervals. When we do the testing, we see that we get true, false, true, false, true. Now, since our original inequality contains an equal sign, we know that as a general rule of thumb, we'll likely include those values on the number line in the solution set by using the inequalities, by using the equal sign in our inequality, unless they conflict with a restriction. So if I was just to look at this, I would say to myself, okay, well, x is less than or equal to -5, and then I would say negative 2.7 is less than or equal to x is less than or equal to 1, and I would say x is greater than or equal to 10.7. But remember that we cannot equal -5 or +1 because those are restrictions. So we can't say less than or equal to -5. We have to simply say less than. And we cannot say less than or equal to 1. We have to simply say less than. And not only that, but we have to get rid of these decimal approximations and put in the actual numbers. So when we do that, before getting rid of those decimal approximations, we have this solution set here and this in interval notation, but of course we want exact answers, so we sub in the appropriate values for those decimal approximations, and we get our final answers as shown. Notice that we are not letting x equal -5, and we are not letting x equal 1, but we are letting x equal -3.5 or 4 minus 3 root 5 and 4 plus 3 root 5. The difference being these two values came from the numerator and aren't restricted, whereas these two values came from the denominator and are restricted. Similarly, when we go into interval notation, we make sure to use a round bracket on those restricted values, but we're using a square bracket on the values that came from the numerator because they're not restricted.